It's 5:30 p.m. in Ho Chi Minh City. A huge rain has been hitting for 20 minutes, and in the next hour, it is expected to shut down a huge district. Hundreds of streets are flooded, and the city is going to lose billions of dollars. Not because that we can't solve it or we lack data, but the data is scattered, slow, and unreliable. That is why we have created FlowGuard. First, I would like to extend a warm welcome to our beloved churches to our presentation. We are AQUAHOLICS in Paris, and welcome to FlowGuard. This is the table of content. Now we will come to the introduction. In round 1, we have created FlowGuard. It is a real-time flood intelligence platform designed to predict, detect, and warn before the flood comes. So instead of just relying on a single source, FlowGuard brings together IoT water level sensors, weather and tile data, and verified citizen reports into one unified early warning system. The problem we are having is that Ho Chi Minh City is experiencing heavier rain each year. This has caused flooding, traffic jams, and more than $1.3 billion in losses each year. Today, the flood information in the city is extremely unclear because the crowd reports have up to 80% noise, the sensors are not connected to each other, and the current system are too slow. The real problem is the lack of a clear, real-time early warning system. And FlowGuard, our solution, is going to solve that problem. It combines low-cost sensor with weather, tide, and movement data, and its AI is going to predict flooding from 5 to 10 minutes before it actually happened, and set instant alert, simple map, and clear advice for users. Now let's come to the business part of our project. Our analysis show that the timing is extremely right because both Hanoi and Ho Chi Minh City are pushing policies that support AI IoT, early warning system in urban flooding. Big cities are losing lots of money, so it is obvious that they clearly need solutions that are effective and affordable, which have created a strong base for our team to build the products. But today's solutions still do not solve the full problem. Because IoT sensors work on their own, mic flood is slow and expensive, social media reports are not effective, and government data often comes late. But FlowGuard is different. It connects sensors, AI predictions, and verifies citizen reports into one system, so alerts are faster, clearer, and cheaper. The market size and benchmark has shown us that this is not just a Vietnam problem, because across Southeast Asia, flooding creates a huge market. Major cities like Ho Chi Minh City, Hanoi, Manila, and Jakarta have similar problems, so FlowGuard is here to fix that. This has led straight into the market gap because even at this moment, Vietnam still has no real-time system that combines rainfalls, tide, sensors, and citizen inputs. All of the problems clearly define the exact requirements city needs, and FlowGuard has them all. Now my teammate Dean is going to talk more about the business aspect of the project.
Citizens rely on slow and unreliable social media updates during floods. FlowGuard provides real-time location-based alerts, a transparent WebGIS flood map, and verified sensor and community photos to help users avoid flood roads and make safe mobility decisions. Logistic fleets suffer from vehicle damage, downtime, and penalty fees during flooding. FlowGuard provides API webhook alerts, a rich dashboard, and AI route optimization. Our confidence scoring system reduces phone alerts and help dispatchers protect assets and maintain OTD performance. Authorities need a unified view of citywide flooding. FlowGuard integrates center data, crowdsourced reports, rainfall, and tidal level into single common dashboard, supporting official warnings, hotspot detection, and resilient planning aligned with HGD 11 and 13. We serve 3 segments: citizens, business, and government. Key activities include sensor integration, AI prediction, routing optimization, and data validation. Key partners include hydrometeorology agencies, IoT hardware suppliers, and city authorities. Our revenue model has 3 streams. B2C is free to maximize adoption and data quality. B2B use subscription, plans tailored to fleet needs, and B2G runs on project contract with annual maintenance fee. For business customer, the journey goes from awareness to advocacy, with key concerns around unclear ROI and integration effort. FlowGuard solves it with an ROI calculator, a sandbox API for quick integration, and a free 3-month pilot to prove real value. Our main KPIs are demo to pilot conversion, integrate time, and pilot to paid conversion. For government agencies, year 1 focus on hardware installation, while later years shift to software and maintenance. We offer 3 tiers: a pilot district at around 74 million Vietnam dong, a city-scale package at 1.7 billion Vietnam dong, and a national rollout of 1 to 2 billion Vietnam dong per province. A city-scale FlowGuard delivers around 15 times ROI over 3 years, with break-even in under 1 year. FlowGuard positioned at high value with low to mid pricing compared to costly hardware solution or basic weather apps. FlowGuard delivers free access for citizens, ROI driven pricing for fleets, city-wide intelligence for governments at a fraction of traditional infrastructure cost. For B2C users, the journey goes from awareness to advocacy, with common barriers like distrust, spam concerns, and hesitation to share location. FlowGuard solves this through simple onboarding, a free test alert to build trust, weekly checks to keep users engaged, and light gamification to encourage reporting, guiding users smoothly toward long-term retention. For business customers, the journey goes from awareness to advocacy, with key concern around unclear ROI and integration effort. FlowGuard solved it with an ROI calculator, a sandbox API for quick integration, and a free 3-month pilot to prove real value. Our main KPIs are demo to plot conversion, integration time, and plot to paid conversion. For government agencies, the journey runs from awareness to advocacy, with challenges like the long approval process, strict data security rules, across-department coordination. FlowGuard addresses this with clear complaints documentation, a single point of contact, fast onboarding and training, and a human-in-the-loop validation, helping government adopt the system confidently and sustain long-term. Our to-go-market strategy follows the AIDA model. We build awareness through seasonal campaigns, spark interest with demo and real case walkthrough, create desire through free pilots and dashboard trials, and drive action with simple onboarding and clear calls to action. We measure FlowGuard across 4 impact areas: urban mobility with 15 to 25% reduction in congestion, economic impact by cutting flood-related vehicle damage and improving OTD, climate resilience through 5 to 10 minutes of early warning with over 85% AI accuracy, and community participation with more than 5,000 verified reports each month. We track 9 social impact metrics, including 15 to 25% reduction in congestion, over 10,000 abort rescue routes per month, lower motorist losses, and OTD improvement. We also deliver 5 to 10 minutes of early warning, maintain over 85% AI accuracy, update 20 to 50 flood hotspots each season, and aim for more than 5,000 valid community reports per month, with 50,000 active users in year 1.
Thank you, Ting. And now, our team will talk about our technical documentation. First, let's take a look through our functional requirements. Our first row contains the 4 must-have pillars, the non-negotiable foundation of FlowGuard, which is core sensing, basic alerting, season reporting, and basic analytics. Without any one of these, the core promise of FlowGuard, reliable flood detection and warning, would fail. Then, we move into the should-have features. They are not required for launch, but greatly increase the system accuracy and usability. Next are the could-have items. These improve user engagement and accessibility, but they do not affect core functionality. Finally, the will not have category defines features intentionally excluded from the pilot phase. For each must-have feature, a user story is accompanied with 2 acceptance criteria scenarios. First is core sensing, with the city water engineer as the main actor. A new sensor must appear on the dashboard within 60 seconds, and if a sensor stops transmitting, it shows a notification after 15 minutes. Next is basic alerting, with daily commuter, the main actor, receive an alert within 15 minutes of a high-risk event near the route, and the user does not receive any irrelevant alerts. And for citizen reporting, with resident is the main actor, valid photo and GPS report receive instant confirmation and enters the moderation queue, and the system dashboard shows the last timestamp when sensor had not been updated for 15 minutes. And finally, for basic analytics, with main actor is an environmental planner, they can export a full month of data, and the system automatically assigns consistent daily risk score. The use case diagram illustrates how different stakeholders interact with FlowGuard system. The 2 primary actors are public users, who access flood-related information, and the admin, who manage system operations. The Gantt chart outlines our full project timeline across 4 major phases: setup and permission, deployment and baseline, system activation and engagement, as well as evaluation. FlowGuard uses an iterative waterfall and agile hybrid model. This model is ideal for flood monitoring, since waterfall ensures sequencing for hardware tasks, and agile drive rapid prototyping and continuous improvement for software. To ensure smooth collaboration, we combine Google Sheets for Gantt chart with Trello boards for transparency, progress tracking, and rapid response to issues. I will now hand over to Min. The Gantt chart outlines our full project timeline across 4 major phases.
I'm Min. I'd like to take a deeper focus on the core system, how we're going to manage potential risks, and our strategy for future growth and mitigation. First, look at the top 5 risks we have analyzed. To install our sensors across the city, we require government approval. The next 3 risks are related to physical impact, causing equipment damage and errors in our data analysis process. And the final one is securing funding for project development to make sure the long-term sustainability of the project. So here are the solutions to mitigate this critical risk. For the approval issue, we need to apply as early as possible to maximize the delay time, along with a high-level letter of cooperation authorized by RIT. For sensor physical durability, we use IP68 standard materials to enhance water resistance, along with regular maintenance and a plan for spare equipment. For data accuracy, a human-in-the-loop system will be implemented. Critical warning outputs will be double-checked by staff, and the AI model will be retrained frequently to improve its precision. Finally, for the funding risk, once the pilot phase concludes, we will produce a detailed report on the cost savings achieved by using the app. Next, we have the detailed layer architecture diagram of our system. The data will be gathered from the edge layer, which includes IoT sensors and some external data, which is then pulled into the system by the connectivity layer. The data is aggregated and processed along two main pathways at the business logic layers. The first path is for risk assessment to generate warnings and alerts. The other path is to create reward points and propose actionable suggestions. On-process data will be persistently stored in the data access layer, which includes two database sections, one for storing predicted risk along with their timestamp and location, and the second for storing other data such as points, actions, and errors logs. Finally, the application layer manages authentication to secure the access and returns the necessary information to the presentation layer. Now, let's talk about the data processing workflow. Data is initially collected by the data collector module and goes through a validation process before being placed into raw data storage. Then it is fed into risk engine. The engine aggregates into formats suitable for the AI model and analyzes it to generate specific risk scores before creating alerts and suggested actions. Subsequently, the processed data follows a parallel path. It is simultaneously sent to the database for storage and used to send flood coordinates to Google Maps. Following this, the real-time map and the final alerts are pushed out to the public users. Crucially, the system receives feedback from users. It is verified and used to create optimized rules that continuously enhance the risk engine performance. Here are all the key components of our project. Our team used OpenAI GPT-5 for the AI model, IoT sensors with LoRaWAN TSM protocol, risk engine, analytic database, API gateway, and real-time map visualizer. So, how does our model operate? When the model is invoked, it performs aggregation and validation based on predefined thresholds, such as temperature below 50 Celsius or water level lower than 3 meters. It is then normalized to form a data vector ready for AI analysis. If any threshold is immediately exceeded, a high-risk alert is generated instantly. If not, the data proceeds to deeper analysis using a radiant boosting classifier. The model then outputs 3 risk scores based on its analysis. As I mentioned before, a human-in-the-loop system is applied for any high-risk scores. Finally, the model has a self-learning and development mode, allowing it to continuously improve after returning output. Here is the selection of our optimal technologies. With connectivity technology, LoRaWAN was agreed upon due to its low cost, durability, and long connection range, but we still combine it with GSM because of its speed and strength advantages. In terms of receiving reports from citizens, my team believes that interacting with existing chatbots will be the most convenient option at the moment, but in the future, the plan to develop a private app and web platform will be implemented. And finally, due to its advantages of being lightweight, low cost, and easy to install, Lightweight AI is chosen to be the risk engine. Regarding the evaluation plan, our team utilizes several methods to quantify FlowGuard impact, along with corresponding supported tools. From that, we have 8 objectives that need to be measured, but mainly focus on reducing damages caused by floods and improving the project system. Each of the proposed objectives is accompanied by specific one-year targets to ensure the system operates optimally and delivers significant benefits to the community. The objective we have set out will bring significant value to the project concerning finance, attract a larger user base, ensure smoother system operation, and enable stronger development. To verify the user base, there are 5 methods for testing with diverse scales, ranging from large community down to individual small groups. This session is divided into 4 phases. Phase 1 focuses on launching and testing, followed by collecting feedback and implementing improvements in Phase 2, which leads to the official release. Phase 3 will involve the initial expansion and commercialization into neighboring provinces and cities, before reaching the final phase, which is scaling up nationwide.
Thank you, Min, for your part. Now let's come to the conclusion. In short, I'll say that FlowGuard is more than a warning tool. It is the foundation for smarter urban mobility and climate resilience. The next phase, we aim to expand from just prediction into intelligent routing, similar to Google Maps, but more optimized and flood safety, which help commuters and businesses choose the safest, fastest path during the extreme weather. from district-level pilots to city-wide coverage, and eventually to regional deployment across Vietnam and Southeast Asia. FlowGuard has a clear roadmap to protect millions of lives and livelihood. These are the references and data that we have used. That is the end of our presentation. Thank you for listening, and I wish you an amazing day.